Okay, so now we're ready to get into the algebra of the simplex method. We will really do all the calculations and get any problem solved. So we're going to give you this example to illustrate the idea. We have a minimization problem with two inequality constraints and two variables. Okay, and the standard form problem can be found by adding two select variables to get these two equality constraints. So we need to keep track of the objective value, right? Because we need to keep improve our solution, and the objective value is certainly the record for the performance. So we're going to denote one variable z to call them the objective value, and that's why the objective value will in some places to be called the z value. Because that we know that we are minimizing z, and all the variables except z must be non-negative. So the standard form can be just expressed with three equalities like this. Okay? The first and the second equalities are just the two equality constraints. And the zeros equality, this one, okay, is just expressing the objective function. This equality tells us how the objective value is. Z is equal to negative 2x1 minus 3x2. And we put that into the zeros row or the zeros constraint. With this, we have a three equality linear system. And we will repeatedly use linear algebra to solve this system. To start, we need to first have an initial basic feasible solution. For this example, we know a basis has two variables or two basic variables, so that AB, the matrix formed by the two corresponding columns, is invertible. And by satisfying AB XB equals B, we have a basic feasible solution. XB must all be non-negative. So in some situations, typically we don't know how to find these basic columns, right? You choose any two columns, you do not know whether they will be linearly independent, and you do not know whether the result, the solution of this linear system, will be non-negative. In general, that's hard, but for this particular problem, it's easy. Okay, for this particular problem, when we need to find two variables to be basic, certainly x3 and x4 works. Why? Because this is an identity matrix. So in the system, because we have this particular thing, so these two columns can form an identity matrix. And if we choose x3 and x4 to be basic, our AB matrix will just be an identity matrix. This is certainly a special case. Okay, not all linear programs have this property, and probably you may think about this. Why do we have this identity matrix? Okay, and we're going to discuss that later. But here we have this, and moreover, in any standard form problem, the right-hand side value must be non-negative. So if we have this, XB would be AB inverse B would be non-negative. Okay, so with that, we can have an initial basic feasible solution, and the basis is x3 and x4. So now let's start from the x1. Okay, our initial basic feasible solution have x3 and x4 being basic, the other two non-basic or 0. Okay, with this, the original objective value is also 0. Now we know we want to somehow move to a better basic feasible solution. So we need to choose a non-basic variable to enter. Here we have two candidates. Okay. In this case, the zeros row is providing us valuable information. What does that mean? We want to know when a variable becomes larger, goes up from 0, what will happen to z? And with this, we can see that if x1 goes up, then z will be smaller. Or if x2 goes up, z will become smaller. right? Because we need to maintain this equality in any time. So this tells us that we may enter either variable because both of them will give us some improvements because we want to minimize z. One thing to keep in mind is that when you are doing so, one variable goes up and the other variable will remain to be 0 because we may enter only one variable. Geometrically, that's because we are moving along an edge and we are only allowed to increase one variable. Anyway, here, suppose we know that both can enter and we choose x1 to enter. So now, with this in mind, we now need to know when should we stop. And as we mentioned, we stop when one basic variable becomes 0. x1 now goes up from 0. 0, 1, 2, blah blah blah. When x1 is 0, the solution is 0, 0, 6, 8. If x1 is 1, then plug in that, we know that x3 and x4 must go down to 5 and 6. Or if x1 is 2, then x3 and x4 must go down to 4 and 4, and so on and so on and so on. And then we can see that when x1 goes up, eventually one variable will become 0. And we want to ask which one will become 0 first. Eventually, x4 will become 0 before x3 does. And we will stop at this solution, 4, 0, 2, 0. Why do we know that x4 will become 0 before x3? And we know that. Why? Because we have the information contained in these two columns. We know that we are increasing x1. Okay? And when we increase x1, x3 and x4 will go down correspondingly. And when x1 goes up, we know these ratios will tell us what will be the result of increasing x1. When x1 goes up by 1 unit, x4 here must go down by 2 units. And originally x4 is 8. So that means x1 can become at most 4 in the second constraint. But for the first constraint, x1 can be up to 6. And that's exactly because we have this competition among ratios. And because 8 divided by 2 is less than 6. So x4 becomes 0 sooner than x3. Okay, we know this because of these two columns or the ratio of these two columns. So knowing that, we will move to x2 with a new objective value. z2 can now become negative 8. If we plug in 4, 0 into here, z would be negative 8. That's good. Okay, so we have done one improvement or one iteration. Now we have a new solution. x2 is 4, 0, 2, 0, another basic feasible solution, which is better. And now we want to move again. Okay, we want to see whether we may improve this solution further. One of these x2 and x4 may enter because now x2 and x4 they are non-basic variables, and we want to ask which one should we enter. Now, according to the zeroth row, we should let x2 enter. Let's read this sentence again. The zeroth row is here. Okay, if we enter x4, it seems to us that nothing will happen. But if we enter x2, that means z will decrease, right? So this suggests us that we should enter x2. And here I'm telling you that what I just mentioned is wrong, okay? But let's assume I don't know that, and I still choose x2 to enter. Then another difficulty will appear. When I enter x2, the second row here saying that x2 can be at most 8 because when x2 increase, x1 will decrease. Okay, so that's something we know. But for the first row, when x2 increase, we don't know what's going to happen for x3 and x1. Okay? When this non-basic variable becomes larger, basic variables may become lower, but here, because we have two basic variables, we don't know what's going to happen here. Okay? And that creates some difficulty. Actually, we know that because we know the second constraint uniquely defines what's going to happen in x1. Okay? When x2 goes up by 1 unit, x1 must go down by 1/2 unit. And that will going to tell us that x3 should also go down by 3/2 units. Okay? But that's somehow complicated, right? If we have 10,000 variables with 20,000 constraints, we cannot get that relationship clearly with the original format. So that's some difficulty. And for us to get rid of that difficulty, one easier way to do is to update the system before we make the second move. Okay? So that in each row there is only one basic variable. The difficulty that we mentioned is because that in the first row there are two basic variables, right? So that when x2 goes up, we need to worry about what's happening in the other rows, and that's going to affect what's happening in the first row. That interdependence should be removed when we update the system. Okay, our goal is to make each row containing only one basic variable. And if that's the case, just as what's happening in the second row, okay, then when we will know that when x2 goes up, what's going to happen to x1, and that will make our life much easier. So we're going to see how to update the system every time when we make a move. We need to do some theory. So we know that this is a standard form linear program. Okay, and given a basis, we may split x into xb and xm, and then we may also split c and a in the same way into different vectors and matrices. So with the split, the linear program can now become this way. We may do some arithmetics. For the second one, xb can be expressed in this way. We take an xn to the right hand side and then multiply both sides by ab inverse. We get this. And then if we plug in xb as this into the objective function, okay, this is something we get. We continue to do some more algebra, we get this. In the objective function, xb disappear because we have plugged in this as xb into the objective function. So in the objective function, there is only xn here. Why do we want to do that? Now let's do some arrangements to get everything aligned. We have z here. Z is expressed by this one put to the same side of z, and then we put that as the zeroth row, just as what we did for setting up the system. And for the constraint, it's still the same thing. But now we put xb and xn to the same side. Okay, here we can see what we want is to answer the following question. We want to know when one non-basic variable goes up from 0, what's going to happen in each constraint in the objective row. If there is nothing here, okay, if xb does not appear in the objective row, then this coefficient exactly tells us what's the impact of increasing one non-basic variable. Okay, if for one non-basic variable this number, this coefficient is positive, then we know this is a good candidate for entering the basis because that's going to decrease z. And also, in each constraint, we can see that only one basic variable would be there, so that we will be easy to answer what's going to happen for each constraint. What's the largest value we may have for that non-basic variable in each constraint. So let's go back to the example. We need to do the following things. Given a basis, we need to update, the new basis. We need to update the system to fit the basis. And there are two things we need to do on the basic columns. We need to make the constraint parts an identity matrix at the first to the nth row. Okay, at the constraint, we need to have this. And for the objective row, there should be nothing related to the basic columns. Okay, all we want is to understand when one non-basic variable is changed, what's going to happen in the objective function and in each constraint. With this particular format, we will be able to know that immediately. Okay, so that's exactly what we want. Okay, so let's come back to our numerical example. Here, originally, the basis is x3 and x4. And then we know that we are good because for x3 and x4, indeed we have this identity matrix and there is nothing related to x3 and x4 in the objective function. And then we know x1 enters and x4 leaves as what we did in about 5 slides ago. And then the basis should become x1 and x3. Okay, x1 and x3, and that means we should update the system to the following. For the second and the first row, we should have an identity matrix, and certainly that doesn't mean the first and the third column should be put together. Okay, here they can be separated, but conceptually the first and the third columns of the first and second row, they should form an identity matrix like this. And also they should have nothing in the objective function. So from this one to this one, how may we do this? Now exactly this is just like Gaussian elimination, right? I give you a linear system and I ask you to make some columns to contain 1, 1 and all others 0. That's what we call the Gaussian elimination process. Okay, so the tool we will use is elementary row operations. So starting from here, I know one task I have is to make this number 1. Okay, I need to make this number 1. So I need to multiply the second constraint by 1/2. By 1/2. Okay, and that's going to give me this equation. And then I multiply the second constraint by -1 and then add it to the first constraint. Why do I do that? I want to remove this number. Okay, after I do that, indeed x1 will disappear in the first constraint and the first constraint will become this guy. And finally I do the same thing to the 0th row to remove this number in the 0th constraint. Okay, blah blah blah, I get this. And the system would be updated from the original one to the new one. Okay, I have an identity for basic variables in the constraints and I have nothing for the basic columns in the objective function. Okay, that's something I want from the old one to the new one. Certainly the solution does not change, right? The solution satisfies first and second constraints, and because we are doing row operations, the solution does not change. But the objective value, the z value, may change because we are using a better solution. Okay, so that's the idea. Okay, so let's take a break, and in the next video I will complete everything.